Okay, kids, so we're back. We're doing some more dynamics examples, trying to show you the really classic ones that have been used throughout the ages in grade 12 physics classes and first year classes. So here's another classic one. What's up, G? So you've got a ledge. And on the ledge, you've got a pulley. Now for us, the pulley will be frictionless. Doesn't have to be. You're going to run into some interesting questions in university physics courses. And here's a mass on the ledge here. And this will be mass number 1. And mass 1 is, let's say, I don't know, 5 kilograms. Sounds good. And let's say that this surface right here has a coefficient of kinetic friction. So there's some friction involved here of 0.05. So it's pretty low friction. And let's say that hanging over the edge here is mass 2. And let's say mass 2 is equal to, I don't know, let's say 10 kilograms. And we're going to assume that this is a one-dimensional problem where the flow of the motion is the positive direction. That's what we're going to assume. So it's still a 1D problem. It's just a 1D problem where the dimension itself is curved. What usually are you asked to find? What's the required usually in these questions? Well, usually they ask you to find the acceleration and the magnitude of the tension or the tension, depending on the question, right? So we have to do some analysis here. And the way you really want to start looking at this is you want to use F net equals ma on each of these. So you would have F net on the first object is equal to the mass of the first object times this acceleration. Net force on the second object is equal to mass of the second object times acceleration. So you've got to find out these net forces. Well, that means you got to do a free body diagram. I like to do them in the given here, but I delayed doing it this time just to show you, look, you need to do it if you're going to do F net. You need to do these free body diagrams. So let's say here we've got tension 1. We've got the normal force on this object number 1. We've got the force of gravity on this object number 1. And we've got the force of kinetic friction on this object number 1. Now, since this is a completely horizontal situation here with object number 1, you know that normal force and the force of gravity, they will cancel out. It's horizontal, like back in grade 11. Then on number 2, object number 2, you've got tension 2 and force of gravity on the second object. Now, having said that about tension 1 and tension 2, we do know that since there's one string here, their magnitudes are equal. Okay, their magnitudes are equal since they're on the same string. So with those free body diagrams done now, we can go into here and say, okay, well, we've got tension 1. We've got force of kinetic friction on the first object. We're not even going to write down normal force, force of gravity. We know they cancel out. Over here, we've got tension 2 and the force of gravity on the second object. There you have it. Let's give ourselves a little bit more space here. Now I'm going to employ that method here where, oops, I want to do that in yellow. I'm going to employ that method here where we drop the vector notation and we look at the free body diagrams to give us direction. Okay? And then at the end, when you do any substituting, you would substitute in positive values. I find it to be very convenient to do it that way. So tension 1, if you take a look at tension 1, we know its magnitude is T for tension, right? Let's just say it's tension, T. So we can write that here if you want. And it's in the positive direction, because if you take a look at this tension 1, it's pulling with the flow. So it'll be positive tension. Oops, let me fix that. And over here, we know that the force of kinetic friction is pulling in the opposite direction, so it's negative force of kinetic friction, and that's M1A. We're going to drop the vector notation. Similarly here, tension 2 is against the flow, so it's minus tension. We know T is the magnitude of it. And this is positive force of gravity on the second object, which equals M2 times A. We're going to drop the vector notation. So let's continue with our work here. We know this would be mu k times the normal force on the first object. And over here, this would be minus tension plus mass second object times g, just the magnitude, and then m2 times the acceleration. Okay, so if you have to pause the video here, and give yourself a chance to take a look at what I've written, and then start the video back up and when you're ready. Okay, so I hope you did that. We're back. So if you take a look at this, let me use red here. Sorry, kids. Acceleration is unknown. Mass is known. The normal force is known because you know the mass of the object. So if you want to even go to a further step here, it's mu k times force of gravity on the first object, because we know they have the same magnitude. I don't care about the direction here, because I'm getting the direction by having imposed it originally. So remember, these are all just magnitudes I'm putting in. And then over here, if you really want to go to the next step, we know that force of gravity on the first object is the mass of the first object times g, and that is equal to m1. Hey, so as I was saying, acceleration is unknown. Mass is known. You know what planet you're on. You know the mass, same mass. You know the coefficient of kinetic friction. And tension is unknown. Over here, similarly, tension is unknown. You know the mass. You know what planet you're on. Mass is the same. And you have acceleration here, unknown. So really, you've got two equations and two unknowns. It's a system of equations. We've done this before. Let's call this equation 1. And we'll call this equation 2. Now, you can solve this by elimination or substitution. There's actually a variety of ways in doing this. I'm just going to add these two equations to undergo elimination. I'm going to add them. So here's equation 1. Here's equation 2. All right. Let me draw an addition line here. Let me draw an addition line here. So plus t minus t, t's are gone. Okay, what do we got here? Let's add these two terms together. M2g minus mu k m1g. Let's add these ones here. M2a plus m1a. So as usual, if you have to take a pause pause the video and go through it slowly at your own pace. That's the beauty of this. So let's continue. Let's continue here. Let's do some factoring here. G factors out of each one. So we have M2 minus mu k M1 is equal to, let's factor out an A here, M2 plus M1. There you have it. Well, that's a horrible M. Isn't that a horrible M? Let's fix that. Do, 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 do. All right, so there's that. I hope I'm not sounding too much like Bob Ross. That just crossed my mind. Anyway, let's continue. So we're going to divide each side by this bracketed mass. So we're dividing both sides by M1 plus M2. So we're dividing both sides by that. We get G M2 minus mu K M1 is equal to acceleration. And remember, I divided both sides by M2 plus M1. Okay, like I said, if you got to pause, pause. All right. And we did analysis, so we're now ready for substitution over here. Remember, we used grass. Okay, so I plugged in the numbers. Notice all the substitutions when you plug in the number with this method, they're all positive. I'm never going to put in a negative 9.8 here. It's all positive. The directions have been taken care of a long time ago when we imposed those positive and negative signs from the free body diagram. So there you have it. There's your acceleration. So the other thing they wanted us to calculate was tension. So we got to take this value for acceleration and bring it back into this equation. Why don't you try that? Pause the video and give it a try, okay? Okay, well, I hope you realize here that if you're going to do this, right, you got this equation right here, equation number 1. You need to bring this to the other side so it becomes positive. Then you can factor out an M1. Substitute, and there's your answer. That's basically the magnitude of the tension. One string. Why is my pen not working? There we go. One string, one tension. Okay, so there's your next dynamics example. I think we'll do one more here. Okay, so this next one, kids, is what we call the classic Newton's third law problem. It's in section 2.3, section question 7. Okay, I want you to read that. I think it's on page 96. Read it first. So pause the video, have a read, and then get back to me. Okay, we're all pausing the video. Okay, so I hope you had a chance to read the question there. So let's get started on it. Let's start with our given G, right? And the whole idea with this question here is you've got 3 objects. So you've got the card at the end, which we're going to call the third object, the third cart. And you've got the cart in the middle, which we're going to call the second cart, or the mass number 2. And you've got the first cart right there. And we're going to draw a free body diagram for each of them. And knowing that we know the masses of each of these. Mass 1 is 15.0 kilograms. Mass 2 is 13.2 kilograms. Mass 3, 16.1 kilograms. And we can draw a free body diagram for each of these. So let's start here, and the first situation is we've got a tension here, right? And it's 35.3 newtons at some angle to the horizontal, some angle to being flat, and that's 21 degrees. So that's that force right there. Then over here, we've got force of gravity on this first cart, the normal force on this first cart. Now let's actually, we can do that for all of them right now, just to get it out of the way. Force of gravity, second cart, normal force, second cart, force of gravity on the third cart, normal force on the third cart. Okay, now you have to ask yourself, yes, I'm listening, what is pulling this third cart? What's the force that's acting on it? Well, it's the tension in the rope here. And that tension on the third cart is coming from a rope that's connected onto the second cart. So we're going to say that that's the force here of 2 on 3. Force of 2 on 3. Well, by Newton's third law, there has to be a reaction force. That's why these are known as Newton's third law problems. The opposite force that's equal in magnitude but opposite in direction and acting on different objects. We learned about that before. So force of 3 on 2, because they share that tension in the string there. And then you have to ask yourself, well, what's pulling this second object? Well, it's the force of 1 on 2. There's a string between them. And then by Newton's third law, we have to have the force of 2 on 1. The force of 2 on 1. So give yourself a chance to let that sink in. You can pause the video. Okay, if you pause the video, I hope you're back, and let's see what they want us to calculate. Well, they want us to calculate the acceleration. And this would be acceleration moving forward here in the x direction if you want. You can put x hat, y hat. So this is definitely all in the x direction. And since they're all moving together, the acceleration of the third object is the same as the acceleration of the second object and same as the first object. They're all moving together. So there's that. What else do they want us to calculate? Well, they want us to calculate this tension in the third, in the last chord right here, which we are calling F2-3, or if you want to call it F3-2, it doesn't matter. And the tension in the middle chord right here, which I'm going to call F1-2, or if you want to call it F2-1, it's the same magnitude. Okay, so they want us to find the magnitude of all of these. That's what it says in the question. They want us to find the magnitude of all these. So that leads us to analysis. Now, the way I suggest you do this question is consider all of the objects to be one object. Imagine this to be so. And this is what we would call the system. This would be the system, and it would be all three masses added together. Does it exist in reality? No, it doesn't, but it's a good mathematical ploy to do this. And then we know that there's no motion in the y. Acceleration in the y direction is 0. Carts don't go flying off the ground or crashing through the floor. So this is all a question of x. So it's all a question of F net in the x direction is equal to mass times acceleration in the x direction. And it also, when we're using this system of idealizing everything together as one object, it really forces us to understand that when we are talking about F net, if we really take a look at Newton's second law, we did this earlier, he was talking about adding up all the external forces. Well, the only external force on this system in the x direction would be right here, tension x. All these other forces here, F21, F12, F32, F23, they're all internal to this setup. So when we idealize this as a system, that's not there. So all that's left here, since there's no friction, we kind of lucked out with that, is tension X. That's all. That is the only external force. So we can put in here tension X is equal to the mass now, not M1, M2, or M3, but mass, the system, right? Acceleration in the X direction. Well, what is tension X? Well, tension X would equal the magnitude of the entire tension. This 35 degrees is right here to the horizontal, so that's cosine if we're doing components here. Cos theta x hat, and it's in a positive direction. So this would equal positive 35.3 newtons, right, times the cosine of 21 degrees x hat. That's what that would be. That's what that would be. So I can now plug that into here as I continue with my analysis and substitution, really, and say, okay, I want to find this acceleration in the x hat direction. It would equal tension x hat all over the mass. Let's give ourselves some room to work here as we really go ahead and substitute in these values. And we would get 35.3 newtons times cos 21 degrees, and it's definitely in a positive x hat direction, all over the mass of the entire system. So we have to add them. So it's what, 15 plus 13.2 plus 16.1, and they're all kilograms. All of them. They're all kilograms. So when you plug that in, you get positive 0.74 meters per second squared x hat. So now we have found the acceleration. So take a pause here, and this would be my solution, right? Better write that down. Acceleration x. That's my solution for grass. So pause and see what I've done, and then we'll restart again. Make sure you pause the video. So the next part of the required here, where's my pen? Come on. There we go. The next part of our we're being asked to calculate is this Newton's third law pair force and this Newton's third law pair force. Well, it's a dynamics problem, right? So as we continue our analysis here for the other required quantities, we're going to do F net equals ma on each of them. So let's start right here with number 3, and this is all in the x direction. Okay, so this is F net third object x component is equal to the mass of the third object times acceleration in the x direction. Okay, so what I want you now to do is, I'm going to pause the video, try to do FNet extraction on object number 2. So try that, and then I'll show you how it works. But make sure you try it yourself. Give it a pause. Okay, I hope you did that. So FNet, second object, x component of those forces is equal to the mass, second object, acceleration in the x direction. Well, in the x direction here, the only force acting on this is F second object on third object, F2, 3. That's it. There are no other forces. So you can do a quick substitution here. And you would get, I think this object is 16.1 kilograms, if I remember correctly. And the acceleration was positive, what was it, 0.74 meters per second squared x hat. So we're going to get a force of positive 11.9 newtons x hat. So we did that one. So let's see what you did for this one here. Let's see if you got force from 1 on 2 plus force from 3 on 2 is equal to mass, the second object, times acceleration x component. And remember, we're looking to solve for this quantity right here. So what we're going to do is we're going to bring this quantity to the other side. There we have it. And now we're ready to substitute. So the mass of the second object, I think it was 13.2 kilograms. Acceleration was positive 0.74 meters per second squared x hat. Now force of 3 on 2. You got to be careful here. Oh, and I even made a mistake there. Did you notice that? That should be a minus sign. Oops the daisy. Let's fix that right now. Here we have it. Okay. If F2 on 3 is positive 11.9 newtons, by Newton's third law, this has got to be negative 11.9 newtons, right? Newton's third law. So you plug that all in, and you get positive 21.7 newtons x hat. And those are our final solutions right there. So there you have it. Some more examples of more complex two-dimensional dynamics problems. Okay, have a great day. Bye.